Thank you for coming to my talk. It's great to be here. So I'm going to talk about the work that we've done at YerevaNN in the domain of chemistry and specifically on predicting molecular properties and solving molecular optimization tasks. So the work that I'm going to present, actually part of the work was accepted to the Machine Learning for Life and Material Sciences workshop at this year's ICML, where one of our team members presented our poster at the workshop. And let me just start talking about quickly about language modeling. So we're modeling the probability distribution over the strings or documents, and that can be written as a joint probability distribution over the tokens that you have, and which is often written in this normalized form, where we write the joint probability distribution as a product of conditional probability distributions. And historically, there have been many language models, starting from rule-based systems, n-grams, and fully connected neural networks, and architecture specifically derived for sequence modeling and language modeling, such as recurrent neural networks. But the architecture that has become very popular in the recent years is, of course, the well-known transformer architecture, which was proposed in 2017. And specifically what we're interested in is the special type of transformer architecture, which is using this idea of autoregression. And the idea is that given a prefix of subwords or tokens, you're modeling a probability distribution over your vocabulary, over the set of subwords or tokens that you have with a transformer. And you make some prediction, and you shift everything one to the right, and you arrive at the same problem. This is good because experimentally you can productively train this kind of architectures on a lot of data, and it also is optimal in terms of data utilization, such that you compute the gradients for each token, as opposed to something like a mask language modeling, where you compute gradient for something like 20% of your tokens that you mask. And this transformer architecture is fully differentiable, and in practice, we're minimizing the negative log likelihood with gradient-based optimization methods. And now let me switch to language modeling on molecules. So there are different molecular representations. One of them is the 3D representation that specifies for each atom of the molecule, it specifies XYZ coordinates, and this configuration has some kind of potential energy that you can compute. And if we think about the surface of the potential energy on these 3D configurations, the local minimum points of this surface are called the conformers of the molecules. Another representation is a 2D representation, and this is good because of graph representation learning, where you can derive or construct translation and rotation invariant or equivariant architectures depending on the problem. That has been very successful. And of course, the 1D representation, which you may guess that is maybe the most compatible with language modeling, because it's essentially a sequence and you can just model it from left to right. And there are many different 1D representations, such as the well-known selfies representation, which is constructed by traversing the graph of the molecule. And as you visit each node, you just write the atom, the corresponding atom. There are other representations, such as selfies, which tries to solve the invalid. In SMILES, you can get basically invalid molecules. It's possible to have some configuration of the atoms such that the molecule is not valid. So selfies tries to solve that, and there are more modern molecular representations, such as SAFE, where it decomposes the graph into fragments and writes the fragments in any order. So you can permute the fragments and the representation the same. So in our work we have used smiles, the simple smiles representation, and just let me quickly illustrate how it works. So you're basically traversing the graph with a DFS traversal, and as you visit each node, you just write down the corresponding atom in the sequence, and yeah, you get your smiles representation. So in order to train this the language model, we constructed a data set that contains around like more than 100 million molecules from PubChem and their properties, as well as interactions between different molecules. So for example, if you want to write the synthetic accessibility score of the molecule, sorry, you just have a special, this, I don't know, I think you can see it, the starting and closing tags, and you have the value inside. And of course, if you want to write a molecule, you just write the corresponding starting token for the molecule, end token, and you just put the smiles in between. And you can do this for different kinds of properties, such as the computed logarithm of the partition coefficient and weight of the molecule, the total polar surface area, the QED, which shows the drug likeness of the molecule, and yeah, we have like some special tags for like generic properties such as vapor pressure, etc. And importantly, we have this similar tag where it tries to quantify similarity between two molecules. And the way that you do it, you just like write the corresponding opening tag for similarity, you put your molecule in, you put the similarity value in here, and you just close it. So this means that this and the main molecule in our sample that have a similarity value of 0.59. Yeah. I don't know why it's showing, but we're also shuffling these properties and the molecules so that we can do like molecule condition property generation and also like properties condition molecule generation. So it works like both ways. So the way that we quantify similarity is that we have this thing called the fingerprint of the molecule. For example, if you have like two molecules, let's denote the fingerprint of one molecule with A and the other molecule with B. It's just like a binary string, and the ith position of this binary string corresponds whether or not the molecule has some specific feature. And the way that we do compute the similarity between two molecules is that we just compute the intersection over union between these two binary arrays, which is written here. Yeah. So we're actually not training from scratch because I should mention that this data set is around like 40 billion tokens. So if you train like a couple billion parameter model, it may not be compute optimal, so we're doing continued pre-training. So we're taking pre-trained models, and one of them is the Galactica model from Meta AI, which was trained on literature and code mainly. It's like a decoder-only architecture, and at the time of its release, it was outperforming the existing models on like benchmarks like Truthful QA and Big Bench. Yeah. Let me just drink some water. Sorry. Yeah, and it also was outperforming the existing models in the mathematics of the MMLU benchmark. By the way, if you have questions, just like interrupt me and ask them. And the second model that we used is the famous Gemma model from Google. And it has like two sizes. One is like 2B and the other one is 7B, and they have been trained on 3 and 6 trillion tokens correspondingly. It's again like a decoder-only architecture, but it's like more fancy. It uses like a rotary positional encodings, and it uses like, I think, RMS norm instead of the layer norm for efficiency considerations. Yeah, and again, at the time of its release, it was performing better than like other models in the MMLU benchmark, as well as in like this Holoswoke and others. Yeah.
I don't understand. As far as I understand, SMAS is the multi-representation of the model, correct?
Yes.
How good of a representation is it? I understand that it's somehow industry standard, but we lose a lot of data on the positional arrangements when we do multi-representation representing encapsulate all of that. I just like try to think if I'm trying to do something like protein folding problem, would it be useful for me?
Protein folding, so I'm not sure I understand the question, the last part of the question.
How good representation?
Yeah, so obviously it has limitations. I mean, this representation is not unique because you can simply try, like, traverse the graph from a different place. But it's like very common to use like SMILES representation with language modeling techniques. So there is this other thing, as I mentioned, it's called the SAFE, where you decompose your graph into different fragments, and then you just traverse these fragments, and then just you put the fragments in your representation to put the traversal of the fragment. So basically you can do something like, you can put the fragments that you want. For example, you can put two different, so you can fix like a fragment here and a fragment here, and you can say just infill in the middle, which you cannot do with SMILES. I mean, it obviously, again, has some limitations, but I think that it's the idea that it's like kind of easily can be modeled with language modeling compensates, like, to some extent.
What sort of information do I lose when I go from 2 dimensions to 1 dimension?
Yeah, it's 2 dimensions. You mean this graph representation, right?
Yes. So when I go to that one in your representation?
I think in this case, in the SMILE representation, you don't lose anything. I'm not like 100% sure, but like most likely you don't lose anything. If you go like, the 2D representation is good, is like, you can apply like graph neural networks to this kind of representations. Yeah, maybe, yeah.
If I understood the question correctly, it's like...
Sorry, can you please use the microphone because you can't hear you?
Maybe I can elaborate.
Yeah, sure.
Can you go back from the 1D representation to 2D representation, and can you go back from 2D to 3D? So that's the question where we're talking about losing the data.
I think, like, I'm not a professional chemist, but like nearly in all cases, you can go from 1D to 2D, but you cannot go from 3D to from 2D to 3D, because, as I said, this 3D representation, so each atom has like x, y, z coordinates, and basically for different configurations, 3D configurations, you can compute the potential energy of the molecule, and it's kind of basically this 3D representation is kind of a continuous space, so which obviously you don't have in like a simple 2D graph.
So you can have multiple 3D that points to the same 2D, yeah, but they're different.
Yeah,
And,
yeah, sure.
those functions.
Yeah. In 3D you have like a lot more information.
In 2D also you may use information about the isomeric. I mean, there are two isomers, and presented by using only 2D, you may lose this information. So not always you can come from 2D to 3D. Yeah, but there is a lot of problems that 2D representation is almost enough something.
Like all these pre-trained model, they have an idea what is smile notation and how to read it, right? So
Yeah, sure. So we're using, first of all, we're using the default tokenizers that come with these models. So I'm sure that both Galactica and Gemma have seen Smile's representation of the molecule in their pre-training data. I think if I remember correctly, Galactica has seen around like 2 million molecules in the pre-training data. Unfortunately, we don't know a lot of information about the pre-training data of the Gemma model. But like, I'm pretty sure there is a lot of molecules in the pre-training data, yeah. So let me just briefly talk about the training technologies that we've used. During the pre-training, we use this thing called Flash Attention V2, which is like, you can think of it as like Torch compiled for attention. And it's very fast. And we're using PyTorches, this fully sharded data parallel V1, which allows you to train like a large neural network on like a cluster of GPUs. So you shard your model across like the number of GPUs you have, and you do distributed training on the GPUs, which like greatly increases the GPU utilization that you have. And by the way, if you're interested in this topic, one of my colleagues is going to talk about in depth about FSDP tomorrow. So please check that talk. Yeah, and we constructed the data set, we've picked the language models, and we trained them, and we call them, we basically prefix them with the chem, the CH, and the Galactica becomes Chemlactica, and Gemma becomes Chemma. We've taken two models from Galactica, 125 million, 1.3 billion, and we've taken the 2B Gemma model. Yeah, and after training these models, you can do simple evaluations. For example, you can input the smiles, input your molecule, and write down the property that you want to predict. For example, the SAS score. Let the model predict the property, and you can compare what the actual SAS value was. Yeah.
I have a question on that.
Yeah.
So when you do the property prediction with the property name token, or CLS, or what we call it, is the prediction, in that sense, a mass token that is being predicted? So is it part of the vocabulary? So for example, if the property...
Yes. So
have you ever, how does that compare to just taking the embedding of the smiles and, for example, running like a regression towards the property, which, have you ever compared that?
no, actually, but I mean, yeah, that's a great question. So first of all, we evaluated on like, let's differentiate between two kinds of properties: the properties that have been in the pre-training, and you may also have like properties that the model has not seen, and you may not have lots of them, and you may want to fine-tune your model on these properties so that your model is able to do predictions. And I would say for the properties that it has seen in the pre-training data, we just do this kind of evaluation, right? Without the regression head. I mean, we actually don't use regression head for the other part, yeah. but there is a paper that actually does this, and I think that they get like better results if you compare it to like let the model generate the output. Yeah, I mean, I guess we're not exploiting that too much. Like we're just seeing like if you do like standard SFT or like standard prediction, autoregressive like decoding of the model, like what are going to be the results. Yeah, but definitely you can do that to get like better performance. Right. And the other task is that you can specify the property that you want and you can decode a molecule, right? And again, you can check if you can compare the property, the target property that you gave and the property that the property of the molecule that the model generated. Yeah, and if you do this kind of stuff for example, SAS score, right? If you condition the molecule on the SAS values, you get a graph like this, where x-axis represents the SAS value that you conditioned with. Every blue dot is a molecule, and the y-axis represents the SAS value of the generated molecule. Does it make sense? Yeah, so the histogram is the histogram of the SAS values that are in the PubChem. You can maybe notice that as you go out of the distribution of the SAS values in the PubChem, the performance tends to get worse. Yeah, the same can be done for total polar surface area. And the same can be done for similarity. So you put a molecule in here, you put the target similarity, you generate a molecule with the model, you compare the inputted similarity with the predicted one. And we can see that it's not like that great at this task compared to like the other ones. Yeah. Okay, if we try to quantify everything, so we have 6 columns here. We have QED, similarity, SAS, C-log P, TPSA, and weight, which are like 6 different properties. And these values represent the RMSEs. And under the PP column, it's the property prediction, where you give a molecule and you predict a property, and the CG is the conditional generation, where you give a molecule and you give a property and the model predicts the molecule. Yeah. And as you asked, so if you want to do like a property prediction that the model that is not in the pre-training, you can take like a data set, such as like a molecule net or ADMET, and you can just do supervised fine-tuning on the training set of this data set, and then just simply do testing, and here are the results. So we can see that we are like marginally same with like the message processing neural network. But I should mention that we do full fine-tuning of the model, right? So for example, if you have like few molecules in the training data set, you may overfit with like a 2B model. Yeah. And here is another evaluation of the property prediction that has not been in the training data, the pre-training data. We take this ADMET data set. We have 4 properties of the molecules. We train them on the training data and test on the testing data. And we can get like more or less comparable results with the existing methods. Yes. Now let's talk about molecular optimization. So in our work, we're formulating the molecular design problems as like optimization problems, where this big M represents the set of candidate molecules, which is like estimated to be like very big. So it's like on the order of 10 to the 16, so it's very large. And this O is like called an oracle function that you want to maximize. So you want to find a molecule from this large space that maximizes your oracle function. And the difficulty is that M is very large, and in like many practical applications, the oracle function is very expensive to evaluate. For example, you may have like as an oracle function a lab experiment or like a quantum simulation, right? Yeah, and there are like different methods that can be applied to molecular optimization. So there are like genetic algorithms where you have where you explicitly define crossover and mutation operations and try to optimize the molecule in that way. You can apply Monte Carlo research where you generate an atom at a time. Important there is this technique called YerevaNN that uses policy gradient methods and uses RNN as its policy, and the oracle function is the reward function. And there are extensions of this YerevaNN technique called like augmented memory and beam enumeration that apply like fancy filtering, memory smiles augmentations, etc., to improve the sample efficiency of the original YerevaNN. And there is another work that tries to utilize the similarity. The similarity, you remember, right? We defined for molecular optimization. And it basically starts with a lead molecule. So you're just inputting a molecule that has a lead. This is like very suitable for lead optimization problems. And you just try to predict molecules that are similar to the lead. And this way you are able to optimize, which brings us to the method that we suggested. So if we let this level curves be the level curves of the oracle function, and the darker colors means that the value of the function is higher. We start with a random or like some specific set of molecules, and as we could generate similar molecules to the given ones, we're just generating similar molecule, and then we do a bunch of those. We evaluate them with the oracle function, and then we pick the best ones, and then we can repeat this process, right? We can generate a bunch of molecules that are similar to the current ones that we have. We evaluate with the oracle, and we pick the best ones. And if you do this a couple iterations, you may hope that you can get like an optimized molecule. So this actually can be interpreted as a genetic algorithm where the crossover and mutation operation are defined by the language model, when it generates basically similar molecules to the given one. Let me just drink some water. Okay, and to formalize this idea, we're just starting with an empty pool. We have some kind of loop, and this with some stopping condition, which can be like if you exhaust all the oracle calls, if you achieve like some objective. And we're taking like a subset from this pool. We're generating molecules, a bunch of molecules that are similar to the subset that we've taken. We're merging the pool and the new generated subset, and we're taking the best molecules and reassigning it to the pool. And we also insert one more step here. So we say if the best molecule doesn't improve for k iterations, we're training the language model on the molecules in the pool, via SFT. So this basically says that if you get stuck, just train your language model on the best current known molecules, such that it basically like this steers the model's distribution towards the molecules that we have, that we currently have, the best molecules that we currently have. And you may ask like why this may work. So there is this idea that I think first was introduced in the Llama 2 paper, where they have some oracle or reward function, and they try to do what's called this rejection sampling fine-tuning, which is that you have some oracle that you want to maximize. You want to give a response that maximizes the oracle function. In this case, it's like a harmfulness of the generated text. And basically they say that if you generate a bunch of answers, you rank them with your oracle, these answers. You take the best answers that you get. If you train your model on the best answers, you basically get improvement in the performance, as you can see here. So they went from like around 50% to 60% in this particular test, right? And let me just talk about some benchmarks. So there is this practical molecular optimization benchmark, which proposes 23 tasks, and it emphasizes the sample efficiency of the proposed algorithms. So they put a hard constraint on the number of oracle calls that you can make. And to evaluate the sample efficiency and the optimizing ability of the proposed methods, they suggest to plot the number of oracle calls against the best oracle calls so far. So like at the ith step, what's your best oracle score that you've achieved so far? And you just calculate the area under the curve of this, And it has, as I said, 23 tasks, which include like similarity and rediscovery based tasks. It includes isomer based tasks, median based tasks, smarts based tasks, and of course multi-property optimization tasks. And it also contains 3 inhibition predictors tasks, which are like classical machine learning models that given a target molecule pair predict the binding affinity, I think. So you're required to, so you need to maximize this prediction value. Right. So a multi-property optimization task may look like something like this. So you're generating a molecule, and the final oracle function is the combination of the total polar surface area of the molecule, the similarity of the molecule, and this hexofenadine molecule, and the logarithm log p of the molecule. Yep, if we look at the numbers, we can see that our method is like better with high margins across all models. Yeah. Okay. And if we try to visualize the optimization trajectory, so the x-axis refers to the number of oracle calls that you have. Every blue dot is like a molecule that you generated. The green dots represent the pool that you had, right? And the red molecules represent the molecules that you trained your language model on. So we see that through time, our method is like starting from like a very low oracle score, and through time it optimizes the objective. And like you may ask, like you've trained your model on like 100 million molecules. Like does it simply retrieve something from the training set and then just give it as an answer? And we've done this experiment to investigate that. So on the x-axis represents the distance from, actually, yeah, the x-axis represents the distance from the generated molecule from PubChem. And the y-axis represents its oracle score. So every dot here is a molecule. These colors represent time. You go black to white. So we can see that during the beginning of the optimization, we have like molecules that are both close to PubChem and far from PubChem, and they also have like low oracle scores. And through time, we're able to optimize the molecules such that they have higher oracle scores and they are far from PubChem. So we can conclude that our system doesn't simply return something, retrieve something from the training set and just give it an answer.
Sorry.
Yeah.
Do you force your model to be out of the training?
No, we don't do that. And there are actually, like, if you look at a simpler task, for example, if you look like, you just basically need to maximize like a similarity metric. Like, by chance, you can get like a molecule in the PubChem that's already similar to this, to the molecule that you're trying to optimize against, right? And in this kind of cases, the model can retrieve something from the training data set, right? Because it's the easiest thing to do for him. If you have something in your training distribution that already solves the problem, I think the model is going to do that first. But in this case, you don't have something that solves the problem. You actually need to maximize the oracle score. So it just kind of goes on its own and like generates new molecules that are not in the training data. Yeah. And like another interesting oracle function can be what's called docking, and for our purposes, it's basically a physics simulation that simulates the interaction between the molecule and target, right? That per target is like some kind of protein, and you want to find a molecule that binds to this protein, right? Yeah, and this docking basically takes your target, your molecule, and gives you like the target molecule or the target ligand complex, and it also gives you some binding affinity, right? And there was a benchmark proposed that was trying to minimize the binding affinity, which was estimated by Autodoc Vina, I think, docking software. And because the docking software is not perfect, right, it may be exploitable, they also add like 2 additional terms in your oracle, such that you also maximize the drug likeness of your molecule. Like, in addition to minimizing the binding affinity, you need to maximize the drug likeness of your molecule, and you also need to keep it under 500 Daltons, right, the weight of your molecule. Because they like found that the oracle function, the docking, can be exploited with like larger molecules. And they formulate an optimization task for like 3 different proteins, and they care about 2 metrics. So if you again plot the number of oracle calls against the oracle score that you have, you care about the number of molecules that have higher oracle score than some specified threshold indicated by this line. It's called the generative yield. So obviously the larger the value of the generated yield, the better. And the other metric is the number of oracle calls required to generate some specified number of good molecules. And this number of the good molecules is defined again with a threshold. If like some molecule has an oracle score higher than some specified threshold, then it's considered to be good. Yeah, and obviously the lower this metric, the better. If we look at the evaluations specifically, considering the oracle burden metric, we see that our method powered with the language models that we trained, like, you can say that it's like twice as efficient, if not more, right? For example, if we look at the Chemlactica 1.3 billion model, so yeah, the existing best method performed like needed 1,000 oracle calls to generate like 100 good molecules, and then we need like 430 And similar arguments can be made for these two metrics as well. And we're like comparable or better when considering the generally built metric. Yes. So like one note on calibration. So like formally defined, like for classification tasks, calibration is we say that the model is calibrated if the predicted probability, like if you say like an answer y with probability p, then the actual probability that your answer will be correct is p, right? And this needs to hold for like all values of p and y. And we have checked the calibration of our models on like a solubility prediction task. And then we see that the models are, I mean, you can claim that they are calibrated on the solubility prediction task. So we basically give like a molecule and we ask it to predict solubility, and we give them multiple choice questions and compare the given probabilities with we basically compute calibration, as I mentioned. Yeah. And if you're interested more, you can read our paper where you can find the detailed training methodology, more experiments, the hyperparameter tuning techniques used, and we have also a fairly minimal implementation of our algorithm, so which you can find at YerevaNN/Chemlactica GitHub repo, where like with like I don't know, less than 10 lines of code you can implement. You can run our optimization algorithm on your preferred Oracle. And I want to say thank you to my dear colleagues and supervisors, and also Nebius AI Cloud that kindly provided the compute to train Chemlactica and Chemma models. Yeah, thank you very much. Questions, please? Yeah.
Did you compare your model with MolBeam, ABTS MolBeam? Are you familiar with it?
A MolBeam?
Yes, it is doing similar thing, molecular optimization in the latent space of learned representation space of molecules.
I'm not sure I know MolBeam, to be honest. Is it like a new
Yes,
paper?
relatively new, yes. We can check, compare
Yeah.
it, it is interesting.
Sure.
Also,
Is it like using ideas from similarity again, or?
it can do any property optimization,
Yeah.
like those, in the latent space.
Okay. Yeah, we'll check that out.
And can you go back to the table?
Sure. Which table?
Go back. This one.
Yeah.
The country. What shows the countries in this?
Yeah. So let me just. So Oracle burden, as we defined, is the number of Oracle calls required to obtain some specified number of molecules. So in this case, that specified number of molecules is 100. So you're looking for the number of Oracle calls that your model requires to obtain 100 molecules that have Oracle score higher than 0.8 in this case. Yeah.
Your numbers are the molecules that you get after 100 calls, or vice versa.
So the numbers, so Oracle burden number is the number of Oracle calls required.
That you get 100 molecules higher than 0.8?
Yes,
molecules?
yes.
Okay.
Yeah.
Have you ever tried to add on like a latent space diffusion to create the conformers to your span strings? Right, have you considered it and then do a lot of
Yeah.
property prediction on exactly the structure of like the energy prediction for the conformation?
Yeah, I think it's a very interesting thing to try, but like we didn't try it.
My question is related to the property prediction task, and I see that you scrape a lot of different values or say results from different molecules and use it in your training and get some results. So, for example, we fix on one prediction property, for example, the logS, and not adding here the arbitrary other parameters, but the parameters that are very related to the logS, I mean correlated. And have you tried this setup? And if yes, will it increase the accuracy of the model?
So let me just repeat the question to make sure I understand it correctly.
So you fix your primary task, which, for example, could be a solubility prediction, or even a high level like biological property prediction.
Yeah.
Then add to the training not arbitrary other parameters that you usually find in a PubChem, but only the parameters or VLC that are correlated with its primary task. For example, we know that log P is correlated with logS, but TPSA is not correlated with logS. So if your primary task is logS, then you should remove preserve log P, but like remove the TPSA and other things which are not correlated, and retrain the model and compare the model with your baseline to see if there is an increase in predictive accuracy.
Yeah, that's an interesting thing to try, but unfortunately we didn't do it. Yeah.
Here.
I would like to ask a question about a task where you provide value of a property to the model and the model generated structure for this value.
Yeah. You mean this one? Oh,
Yes.
no, sorry.
And no, it's okay.
Yeah.
And model generates smiles for you.
Yeah.
But not every smile is a valid chemical structure.
Yeah.
What did you do with invariant structures, and what is a level of such invariant structures in models output?
Yeah, so like we're actually evaluating our model on like, so for example, to get these numbers, we're evaluating our model like on 200 molecules. So you for example, to predict, to calculate this, the conditional generation based on C log P, right? You give C log P value and you just generate a molecule, right? And your question is like, how much of the time the generated molecule is like an invalid molecule, right?
How many invariant smiles the model generates?
I mean, the number is pretty low actually. Like if you condition it like with some value and you generate like 300 molecules, like one molecule may be invalid. Yeah, on that order. 1, 2.
Very, very interesting. And the second question, okay, if the smile is valid, it doesn't mean that the chemical structure is really exist or may really exist.
Yeah.
And in your results, how do you check that generated structures are real, make sense from chemical point of view? And maybe before I answer this question, some small comment about your presentation. It would be really interesting to see a real chemical structure when you speak, for example, about winners in some optimization. Because you speak about chemical structure, but about molecules, but didn't show any chemical structure here. Like this.
Yeah. Yeah, I see the comment. So the earlier question was, can you please remind me?
Are you sure that your winners
Yeah.
Really exists.
Yeah, okay.
How do you check
So-
that this is real chemical structures?
So, in the optimization problems, we basically rely that on the oracle function, right? We'll rely, like we kind of bear that responsibility on the oracle function. We just assume that if the molecule is not realistic, oracle function will just give low values to these molecules. Yeah, that's the idea. But we don't have like any explicit checks. Yeah.
Thank you.
So I have a short question. What the biggest size of molecule you can get from your methods?
Yeah. So I think the training molecules, right? The PubChem molecules are like, I think 90% of them has, if I remember correctly, molecular weight less than 500 daltons. And it very much depends on your training data, right? So if you train like on molecules that have like higher weight, you're more likely to get molecules that have, the model will be more likely to generate molecules with high weight, right? So in our case, I would say that most of them are probably less than 500 daltons, the generated molecules. But I think if you want to like increase that number, you can add like larger molecules to your training set. Yeah. Thank you very much.